Hello and welcome to the 8th European Conference on Space Debris. My name is Nina Patzig and I am head of the Berlin office of Genius, the conference service provider. I have the honor of guiding you through the conference and all 4 content-packed days. Unfortunately, contrary to the original plan, the conference has to take place completely virtually. The coronavirus and the associated restrictions are beyond our control. We would have wished for a face-to-face meeting with all of you, but this decision had to be made to keep everyone safe. But on the bright side, every participant saves travel costs and valuable time. You can follow the conference from the comfort of your home or office and thus also reduce the conference's carbon footprint. I am happy that over 400 participants from countries all over the world have registered for the conference. Today, we start with introductory words from Tim Flohrer, head of ESA's Space Debris Office at ESOC in Darmstadt, Germany. Then I'm looking forward very much to the opening remarks of Director General of ESA, Josef Aschbacher, followed by Rolf Densing, Director of Operations and Head of ESOC. This will be followed by the premiere of the space debris movie Time to Act. Holger Krag, Head of ESA's Space Safety Program Office, will close the session with his opening talk. We are looking forward to these contributions. And now, I would like to hand over to Tim Flohrer for his opening remarks. The floor is yours, Tim.
Welcome to the 8th European Conference on Space Debris in virtual format. We meet every 4 years in this forum, and many of you have been attending the conference for several times and came to Darmstadt in spring. This year everything is different. We are meeting fully virtual. This has not been our plan, but it allows us to cope with the current restrictions. It also allows us to keep with the high demand to attend the event, beyond the capacity of the ESOC conference rooms, and we are happy to host a record number of talks and posters this time. Still, we will certainly miss the opportunities for networking in person, during the coffee breaks, and also in the Darmstadt pubs. Today, all of us are witnessing live how important the access to connectivity is in order to share information. And indeed, information flow and global exchange has very much accelerated. The new situation, and likely also the new normal, also made it very visible to everyone how dependent we are on a functioning infrastructure. Space debris is a major threat to the sustainable use of space as a resource. And space is a precious and limited resource where we can deploy and operate such a vital infrastructure. For our conference, we are going to try out many new and innovative ideas to share knowledge and ideas this week. The current crisis caused by a virus has led to an unprecedented transformation in changing our behavior and how we use technology. And as an organizer of the 8th European Conference on Space Debris, it is my sincere hope that this conference will contribute to managing space debris and space traffic. Let's approach the situation with technology and also by linking the adequate policy concepts. We need to achieve this before we see a space debris crisis setting in, a crisis that our models already predict to happen in case we do not adapt to the evolving situation. This conference is only possible because you, the more than 400 presenters and attendees, are ready to share findings and to dedicate time. And it's possible because we have received an outstanding support by a scientific committee that discussed and selected the submissions for the program. I'd like also to acknowledge the excellent support of our partners, ASI, CNES, DLR, UK Space Agency, COSPAR, IAA in making all this possible. We are seeing a record number of submissions and arranging the about 140 oral and more than 100 poster presentations, and paying attention to the time zones of speakers, hosting the needed tools, and solving all the little and not so little issues is only possible because a number of colleagues have been working on preparing for this event for quite some time. So to all of you, presenting, attending, supporting and organizing this event, a warm thank you. And now, I wish you all a successful week, full of new insights, new ideas, new collaborations and inspiring discoveries. And I will get back to you on Friday for the conference closure, reporting on the main findings of the conference.
Distinguished colleagues, dear friends, ladies and gentlemen. Unfortunately, I cannot be with you today, but I wanted to convey my best wishes for the 8th European Conference on Space Debris, a topic of utmost significance. The European Conference on Space Debris is the largest dedicated gathering on this subject. Internationally renowned scientists, engineers, operators, industry experts, lawyers, and policymakers meet here to discuss different aspects of space debris research, including measurement techniques, environment modeling theories, risk analysis techniques, protection designs, mitigation and remediation concepts, and standardization policy, as well as regulation and legal issues. The first conference of this series was held in Darmstadt in 1993. Today, we are opening the 8th edition. Its scientific program comprises 4 days of 28 sessions with a total of 140 oral and more than 100 poster presentations in virtual format. These numbers show the huge interest space debris attracts, and there are good reasons for that. We are seeing drastic changes in the use of space. There's an ongoing development of large constellations. We have now more active than inactive satellites in orbit, and the forecasts are that we will continue to place around 1,000 new satellites in orbit every year. The effects from large constellations are clearly seen in the collision avoidance statistics. As an example, the ESA Collision Avoidance Service now reports that about 50% of all close approaches of ESA-operated missions are with constellations and small satellites. This is an urgent call for more automation and coordination between operators, and also for increasing efforts in developing the related technologies and advancing in defining policies. Uncontrolled re-entries of space objects will also continue and introduce a risk on ground that must be managed. The number of these events will unfortunately keep increasing. The general compliance with existing space debris mitigation guidelines is improving, but it is still far too low in LEO. Even with full compliance, there's a need to actively remediate the environment by taking out massive large objects, the ones with the potential to create large numbers of small fragments, each of which could lead to a next catastrophic fragmentation. Against this backdrop, global efforts for space surveillance, for monitoring space debris and cataloging orbits are accelerating. Commercial entities enter the scene. Industry, academia, and governments agree that space debris is moving from a research field in the industrial practice. Still, in Europe, there is high dependency on relevant data from the United States. ESA has taken up the associated challenges. ESA's technology strategy includes the goal to invert Europe's contribution to space debris by 2030. With the Space Safety Program, which started in 2020 after subscription at Space 19+, ESA now has the largest R&D program on space debris probably worldwide. Under Space Safety, ESA is commissioning the world's ever first debris removal mission. ClearSpace 1 will be the first space mission to remove an item of debris from orbit. It is planned to be launched in 2025. The mission is being procured as a service contract with a startup commercial consortium to help establish a new market for in-orbit servicing as well as debris removal. Moreover, ESA is developing technologies for automating collision avoidance and improving coordination among operators under the Space Safety Program. The major upcoming challenge, not only for ESA, is space traffic management. Technology and commercialization are advancing fast and drive legislation. Data, open formats, and access to technology are urgently needed to support regulators. In space traffic management, we need to address three major topics. First, ensuring safe operations. Second, facilitation of close proximity operations. And third, supporting ground and space-based infrastructure. ESA is available as space traffic management architect to research, develop and demonstrate technologies and services in cooperation with national and commercial stakeholders with a focus on sensor capabilities, novel approaches and product interoperability in order to support service developments. The 8th European Conference on Space Debris will be an important stepping stone in this regard. Europe in general and ESA in particular are ready to contribute their share in order to make space a safe environment for the benefit of citizens in Europe and across the world. Thank you very much.
Hello and welcome to everyone joining the 8th ESOC Space Debris Conference from wherever in the world you may be participating. I am Rolf Densing, Director of Mission Operations at the European Space Agency and the head of ESOC, the European Space Operations Center in Darmstadt, Germany. I would certainly have preferred to welcome you in person at ESOC, but obviously we are living through unprecedented times with this pandemic. If there is one positive aspect of a virtual conference, then it is the fact that this time we can accommodate a larger number of people virtually than our usual conference facility at the European Space Operations Center can hold. This conference is continuously growing since our first edition in 1993. I understand we have more than 450 registered participants today from 38 countries, making this event the largest of its kind on a global scale. For this opening session, we have on top invited the press to attend, who I warmly welcome and thank you for translating our language, which is at times a bit hard to understand, into interesting stories for the public. I would like to thank and congratulate the organizers of this event for bringing the community together and to make it happen, despite of the circumstances. With this pandemic now entering into its second year, everyone of the general public and everyone who flies spacecraft, who builds and operates ground segment and who develops technologies for mission control has to adapt to enormous challenges that none of us would have predicted at the time of our last Space Debris Conference. I guess over the past year, we have seen more innovation in space operations than probably the 10 years before. On top of the pandemic, the entry of new spacefaring actors and most of all, the rapid increase of objects in orbits around us contributes to making our lives and certainly this conference really exciting. At ESOC, we have taken extraordinary steps to ensure that our fleet of spacecraft keeps flying and delivering their data. However, collision warnings are steeply increasing and we are flying one collision avoidance maneuver on average about every 2 weeks. For some reason that typically happens on weekends or during night, but ESOC never sleeps anyway. Aside from LEO business, we are also operating astronomy and planetary missions involving interesting maneuvers on their way, for example, towards planet Mercury or the Sun, like our BepiColombo or our Solar Orbiter spacecraft. Aside from mission operations and the related ground segment engineering, we are managing what we call the ESA Space Safety Program, the goal of which is to build resilience against hazards originating in space, such as space weather, near-Earth objects, and space debris, of course. As part of this program, we have recently signed a service contract with the Swiss startup ClearSpace, asking them to remove an ESA-owned piece of space debris, which is a Vega payload adapter of the Vega rocket, from an 800-kilometer orbit by 2025. This is the first time that a real piece of space debris is removed from orbit. Independent of this project, however, and through our clean space activities, ESA is committed to neutralize its balance on space debris from 2030 onwards. This means that more objects will return from orbit than we will newly launch into orbit. Our Lagrange mission is set to launch in 2025 towards Lagrange point 5, where nobody has ever gone before, and this will establish an operational space weather observatory in L5. We are doing so in a joint and complementary effort with our US friends from NOAA and NASA. They would go to L1, ESA will go to L5, and both missions will carry cross-calibrated instruments on board. And with our HERA mission, we will be part of a joint NASA-ESA effort to demonstrate reflection of a small asteroid for the first time ever. I would like to thank, in particular, Tim Flohrer and his team for making this conference happen. Thanks to all of you for joining and for engaging in making space more sustainable. Together with all my colleagues at ESOC, I wish you a successful conference, and I'm looking forward to a fruitful exchange. Thank you all for your attention.
Thanks for all the opening remarks. I would like to continue and give you an overview of the program schedule for the following days. Please note that the latest version of the program is displayed on the conference website. Here you can find all available information about the sessions. Please also take a look at the news section, News and Help, for current notices. Every conference day, with the exception of today, will start with 2 parallel oral sessions that will have individual chairs to introduce the topic and presenters. At noon, there will be a moderated panel discussion followed by, again, oral sessions. The days 1, 2, and 3 end with a 2-hour poster session. Because we have participants watching from all over the world, different time zones might come in our way. Because when it is 9 a.m. in Germany, it is in the middle of the night across the Atlantic Ocean. But we nonetheless hope for strong participation in the sessions. Before we dive deeper into the program, I want to encourage you to have patience if the stream should pause. If it does not play after a while, then please reload the streaming page. As mentioned before, there will be 2 parallel oral sessions each. You can switch from one channel to the other by selecting Stream 1 or Stream 2. All participants can ask live questions via the chat tool during these sessions. Please note that all chairs, oral presenters, and poster presenters should be in their area of action at the right time to guarantee a smooth program flow, especially for the live Q&A sessions. One word about the panel discussions. All the moderated discussions will be open for questions from the audience as well. So please get involved and ask your questions. The poster sessions will take place in a special digital platform and will give all participants the opportunity to network. All posters will be open at all 3 sessions, and there will be live presentations of poster presenters. This goes out to all poster presenters. If possible, please be there every time and stand by your poster in this virtual world. The platform for this session is called GatherTown. Every participant gets to choose an avatar and will move around in digitally designed conference rooms like figures in an 80s computer game. If approaching other avatars, one can start a video conversation or chat. If your avatar gets close to a highlighted area, you can get more information or get into action there. For instance, if you approach a table or poster area, you can there form an individual group to have a private conversation. Just before the poster session, I will give you some more advice on GatherTown. Recordings of the opening, all sessions and panels will be available the week after the conference. We will publish the link on the conference website. But now, it's time for me to announce a first highlight of the conference, the space debris movie Time to Act.
Is space debris still a problem? The answer is unlikely to surprise the many experts in the field and the audience today. Yes, the problem is still there. The real question is, why are we acting slowly and are countermeasures devised a decade or more ago still sufficient for the next years, or even today? This question will feature prominently during the talks and poster sessions presented during the next 4 days. But to raise awareness, understanding, and even collective ownership of this environmental problem, it is of importance to communicate where we come from and where we are heading. To do this, Benjamin Bastide-Virgili and Jean-Jacques Biel-Loquet took lead of a group of space debris experts and gifted communicators to create a movie for you and the audience of the next few years to come. Do take a moment to make yourself comfortable while I wish you many fruitful exchanges, new insights, and a pleasant virtual experience. Without further ado, let's start the action.
Once upon a time, the people on a very special planet made their first journey into space. The mission was a success and began a new era for the now spacefaring civilization. Just a few decades later, the pale blue dot had become surrounded by thousands of spacecraft doing extraordinarily meaningful work, studying the changing weather down below, providing information to save lives during disasters, and delivering global internet, communication, and navigation services. But something bad is coming that puts all of this at risk. An accidental collision will create a huge cloud of fast-moving debris. A cloud big enough to spread and destroy further satellites in a cascading effect, creating more and more dangerous fragments until the most useful orbits around Earth are no longer safe for spacecraft or people. Before things got too bad, an international committee was set up to address the growing problem of space debris. At that time, spacecraft were being launched without any plan for what to do at the end of their lives, meaning they would one day become debris, potentially crashing, exploding, or falling down to Earth. To fight back, the committee published the first ever space debris mitigation guidelines. To prevent explosions, at the end of every mission, all fuel stored on board spacecraft must be expelled, and batteries should be disconnected from solar panels so they no longer recharge. All satellites flying in low Earth orbit, below 2,000 kilometers, should be deorbited within 25 years following the end of their mission. To do this, operators need to ensure enough fuel is left to fire the thrusters and gradually reduce the spacecraft's altitude, finally causing it to re-enter Earth's atmosphere and safely burn up. Larger spacecraft are often made of big components that could survive re-entry and reach the ground. They therefore require a controlled re-entry, meaning operators ensure the satellite re-enters Earth's atmosphere above specific uninhabited regions. Earth re-entry maneuvers are very fuel expensive and therefore not practical from higher altitudes. Instead, when the mission ends, these satellites should raise their altitude to be left in a graveyard orbit, preventing them from striking functional satellites in this highly productive space highway. Moving spacecraft to these dead zones does not solve the problem of space debris, but for now, it minimizes the risk to functioning satellites. By following these and other simple steps, the amount of space debris in Earth's environment could be kept at sustainable levels, and the future use of space would be secured. Are we, the people on the special planet, following our own advice? It took some time for the guidelines to have an effect, because many missions had been launched already, or were years into development and would need to be completely redesigned. The first major satellite collision unfortunately took place between an operational and a dead satellite. Crashing at a relative speed of nearly 12 kilometers per second, it created thousands of bits of dangerous debris. Multiple exploding rocket parts, and the intentional destruction of some satellites continued to vastly increase the amount of debris in orbit. By the late 2010s, satellites in high-altitude, economically valuable orbits like the geostationary ring, used for communication services, had near-perfect adherence to the mitigation guidelines. But in low Earth orbit, 80% of satellites that should have performed a deorbit maneuver were left undisposed of and abandoned to their fate. Long-term simulations show an exponential growth in the number of objects in space, and a considerable increase in the number of collisions and debris fragments if space agencies, companies, and other satellite operators don't change their behavior. Today, satellites move out of the way of debris fragments multiple times each year through expensive collision avoidance maneuvers. The United States, and increasingly other countries, use an extensive network of debris-detecting sensors to issue hundreds of collision alerts every week for satellites flying in low Earth orbit, including Europe's vital Earth observation satellites, monitoring our planet's land, seas, and climate. Upon each collision alert, extensive work goes into determining the chance of a collision, as well as deciding how best to protect each satellite, how far to move it, and in what direction. If an avoidance maneuver is carried out, the satellite's instruments are often turned off, meaning they can't gather scientific measurements or provide commercial services. Precious fuel must also be used, shortening the lifetime of the mission. These maneuvers are time-consuming, expensive, and complex. But they are nothing compared to what is coming. The era dubbed New Space has begun, and the number of small, privately owned satellites is increasing dramatically. Thousands are being launched in large constellations, huge clusters in the sky working together to provide more efficient, consistent, and reliable services. Several companies have started launching large constellations into low Earth orbit to provide global internet access, and other companies have similar plans to follow. We are now moments away from having more working satellites in orbit at the same time than have ever been launched before. Such constellations have the potential to bring great benefits, but they could also be a source of huge disruption if we do not change the way we act. The current approach to avoid in-space collisions will be impossible in just a few years, and in this new era, even complete compliance to the mitigation guidelines may no longer be enough. We need to do more. Our future in space depends on automated collision avoidance, from assessing the likelihood of a crash to sending the commands to a spacecraft to get out of the way. Automated decisions could even take place on board satellites, informing operators and other satellites of their actions to avoid interfering with planned maneuvers. As these intelligent space systems get more data and experience, they will become even better at predicting how situations evolve, reducing errors as well as cost to missions. ESA is developing technologies for an automated collision avoidance system, as well as methods of refueling, repairing, and upgrading satellites in orbit, extending the lifetime of missions, and potentially minimizing the number of new satellites that need to be launched. ESA is also working on debris removal missions that will fly up to dead spacecraft and debris objects, capture them, and move them to safety, either by sending them down to burn up in Earth's atmosphere or out to the graveyard zone. Solar sails, balloons, and other devices could be added to spacecraft closer to Earth, meaning they catch more of the planet's thin atmosphere and gradually slow down, lower in altitude, and burn up safely. To promote sustainable behavior, the first international space sustainability ratings are being developed to rate planned missions on their potential for debris creation and adherence to international standards, ensuring activities in space can be openly monitored so we can all assess the environmental impact of missions launched to orbit. Our planet is unique, and the rapid and remarkable development of space technologies has allowed us to see this in incredible detail. By reaching into space, we have brought huge benefits down to Earth, providing technologies that enrich our societies, connect people in previously unimaginable ways, and give us an incredible perspective and understanding of our planet. The orbits around Earth, however, are a limited resource. We must extend all that we have learned about the need to take care of our planet up into space. We know what will happen if we continue on our current path, but we also know exactly what we need to do to change that fate. It is time to act, to ensure humanity's access to space is guaranteed for future generations.
Now we will hear the opening talk of Holger Krag. He is head of ESA's Space Safety Program Office at ESOC in Darmstadt. His talk is about the Space Debris Challenge and ESA's response. ESA has prepared a new program that aims for Europe to ensure European autonomy in accessing and using space in a safe and secure environment. It is about the protection of our planet, its inhabitants and assets in space, and on Earth from hazards originating in space. He will present his program and will give insights into CREAM, one of the flagships of the program.
Good morning, dear colleagues. It's an honor and pleasure for me to present you with ESA's response to the Space Debris Challenge. And ESA's response is something that is prepared ESA-wide, and the gratitude goes to my colleagues Tim Flohrer, Luisa Innocenti, Rosario Nasca, and Alexander Zucek. Now, before coming to the response, let's take a look at the challenge first. What you see here are all objects above 1 meter size. We believe 6,000 of them to be out there. These are the number of objects above 10 centimeter size, roughly 30,000. And a good share of these can actually be seen and tracked from ground, which provides very important and essential input to space operations as we conduct here in ESOC. Red dots represent spacecraft, yellow dots represent upper stages, and blue dots present fragments, so pieces of upper stages or spacecraft. These are objects above 1 centimeter size, and we believe the number to be around 900,000. And you see here clearly the two polluted regions. The LEO region up to 2,000 kilometer altitude, where 2/3 of the objects are, and the geostationary regions. So the two regions that we heavily use are also the two regions that are most polluted today. And when we come to even smaller objects above 1 millimeter, we count roughly 150 million. And even these can be hazardous, as we know ourselves in ESA, because Sentinel-1A, which is one of the largest spacecraft we are flying here, suffered from an impact of a 2 millimeter object into the backside of the solar array, leading to this circular damage here of roughly 40 centimeter diameter. Now, this object was, of course, too small to be avoided, but the fragments released due to the impact, they are large enough to be tracked, and they triggered already conjunctions and alerts with other objects, and also in ESA's fleet. Now that puts the first challenge, namely the tracking of the space population, which is done today by powerful surveillance systems on ground. And what you see here is an overview over the so-called catalog of space objects tracked by these surveillance systems, amounting to an overall number of on-orbit objects of roughly 28,000 today. Below you see the number of spacecraft with a more or less steady linear increase. Only in the latest years we see a change in the space traffic, but more dramatically you see all the other objects, which are mainly fragments, mainly explosion fragments. They are generated by particular events, for example, by deliberate anti-satellite tests that happened in 2007, or an accidental collision between two spacecraft that happened in 2009. Now, this is the challenge and the situation that we are facing today. 28,000 objects, or if you want to put it in terms of mass, 8,500 tons of accumulated on-orbit mass, and 88,000 square meter of geometric cross-section. And the geometric cross-section is relevant for the collision probability. And to give you a comparison, 88,000 square meter of cross-section correspond to roughly 12 soccer courts. Now we have to keep track of them, and we need to measure them. And this measurement is a challenge that we would have to conduct both for the LEO region and also for the GEO region. For the large objects, we do have powerful surveillance system, primarily in the US, but also in Europe. We are bundling efforts, and there are also private and academic efforts that help understanding the population of above 5 centimeter and provide full orbit information. So not only individual detections, but measure the full orbit, which is important for predictions of object position in the future. And objects above half meter size in the geostationary region. Now ESA is adding efforts in seeing smaller objects, and of course here we will not be able to provide full orbit information, but we can at least do statistical counts to shed some light on the numbers and the orbital distribution of these objects by using retrieved hardware from space, in situ detectors, both in GEO and in LEO. But furthermore, we would like to come to the uncharted terrain of 1 millimeter sized objects, which are too small to be seen from ground, and which are not numerous enough to be seen by in situ detectors. And here we are using special observation modes of radars and telescopes to get as close as possible to it. And we would also like to launch an optical sensor into space that can actually see these objects from orbit in the vicinity of 100, 200 or a few kilometers, and then even millimeter-sized objects can be detected and counted for the first time. However, ESA also plays a role in the space surveillance and tracking technology. Here, we are not playing the role of an operating entity, but as a provider of technology. And thanks to the Space Situational Awareness Program, we have been providing and testing technology for bistatic and monostatic phased arrays, radars, both in continuous wave and pulsed mode. We are currently deploying also technology for robotic telescopes that can be remotely operated. This is a deployment site here in Chile, it's La Silla, where we deploy our first half-meter telescope as we speak. But all surveillance systems also have a common need, and that is the processing of the information from tracklets into actual orbit information to products like conjunction alerts, re-entry alerts, and so on. And this can be done also in a concerted efforts by pooling all software developments into one community, into one piece of software that we share Europe-wide. Another focal point is laser technology, which is something I will come back to in a second. Now, let me talk about the next challenge, which is collision avoidance. Now, with ESOC being an operational center, collision avoidance for us is a daily matter. We have a fleet of 20 spacecraft here that we monitor closely since 20 years. This is an example of our collision avoidance software where one of our spacecraft, Sentinel 1B, is approached by a fragment. In this case, we achieved a record collision probability of 150, and obviously we did collision avoidance maneuvers in this case. Several hundreds of collision warnings in a day are processed. A collision avoidance maneuver in ESOC is conducted roughly every 2 weeks. And in this center here, 10 years ago, we have been meeting up with the operator community and also with the surveillance community. You see here people, both civil and also military, to discuss what the content of a conjunction data message should be. And that was one of the stepping stones towards the today very successful conjunction data message. And I think we need this concerted efforts again for new challenges coming with the new space traffic. Now, as a collision avoidance operator, we know that conjunction alerts are taking efforts. Every collision avoidance maneuver means loss of fuel, loss of manpower, and perhaps even loss of data. Several hundreds conjunction alerts are received in a day and need to be processed. And of course, practically all of them are false alerts. So we do have a problem of limited accuracy. It is due to the uncertainty in the information that we get so many false alerts and therefore so many useless maneuvers, which make our life difficult and operations costly. And here I would like to bring up a new aspect of SST, which not only looks at expanding catalogs to ever smaller objects, which is very important for safety of spaceflight, but also into the accuracy of the object. The more accurate the orbit information is, the less we will have to maneuver. And this is something discovered also, it's a niche, if you will, discovered by also commercial systems, because more accurate data than the public available one provides an added value that customers could pay for. And more accurate data can be achieved by more accurate ranging with using smaller frequency. Of course, all the other sensor operating aspects come on top of that. And here the laser could be a fundamental role in the future. And therefore, let's take a closer look at laser. The use of laser ranging has been something for the scientific community so far. The satellites observed are equipped with laser retroreflectors, and this is now changing. Since a few years, it is also possible to use lasers with uncooperative targets, debris that does not have mirrors or retroreflectors on board. The trick is to use several hundreds or thousands of pulses in a second, so that we make sure that at least one or two of them are actually returned to the telescope by the target that reflects randomly. And this is one result. You see here sub-meter ranging accuracy in these residuals, in this case for an upper stage, where you not only see, due to the sub-meter resolution, the dimensions of the upper stage, but you also see the rotation period and therefore gain important information on the attitude motion. Now, if you want to do that systematically and keep information up to date on that high level, you would need to connect several laser stations and work together and hand over from one station to the next. But that means you would need to do these laser observations at all times, which also requires the objects to be seen by the laser in daylight. And also here, since a few months, we have a breakthrough where this was done by institutes in Europe. And these are very promising results that make us optimistic that in a few years we can have laser accuracy information for quite a subset of the catalog. But our dream goes further, because if laser power is further increased, this will also increase the light pressure obtained by the telescope, by the object. And the light pressure will produce a force that would slightly move the target. And I'm not talking about a laser weapon, I'm talking about a laser with a power of a few kilowatts and the power density received at the target of maybe 1 kilowatt per square meter. That's exactly the radiation power of the sun. So it's not more than sunlight, but directed. And that could be enough after a few minutes of radiation to produce a delta V of 1 or 2 millimeter per second, which is not changing the orbit a lot, but which could change the orbit just enough to avoid a collision, in particular a collision between two non-cooperative objects, which is, of course, a very interesting thing. Now, there's another challenge, and that is the change of space traffic. We were used to see conjunctions between our spacecraft and debris, mainly fragments, which is difficult enough, but at least the decision is easy, because the decision is only taken by us, by the one who can actually avoid the collision and active maneuvers. However, due to the change of the space traffic with ever more active objects in space, in the last year we saw already 50% of the conjunctions actually caused by other active satellites. And then that, of course, brings two challenges. First of all, we have more work to do because of more objects, which means we need to automate the process. However, these are expert processes, and it's an expert brain doing a decision to avoid a maneuver, to avoid a conjunction or not. And we are trying to work with industry and expert community outside to automate this process, for example, using technologies like artificial intelligence. But the coordination with other active satellites brings another challenge, because here you cannot act unilaterally and just automate. You would have to communicate your decisions, or at least your plans. Standards are required. We need to meet up with the community, but not necessarily rules are required, because it could be left up to the machines and an optimization process to prepare a decision, like it is done in aviation, and present a readily decision to the operators to take. And this is something we are working on in order to save workload for all of us. Now let's come to another challenge, and that is the prevention of debris. Now, before going into this, let's look at the space traffic originating from Europe as compared to the space traffic originating from other continents, which you see here in this diagram. You see that Europe does not rank very high, which also means that action taken by Europe would not be very effective if not similar actions are taken also elsewhere. And therefore, we are putting our bet on international collaboration. And a body where we have been a founding member of is the IADC, the Interagency Debris Coordination Committee, which also meets up in Darmstadt from time to time. These are engineers, not politicians, but engineers that compare the effectiveness of debris prevention solutions and then produce so-called guidelines. And these guidelines are of common practice use today. They stipulate, for example, for all objects that they, no matter where they are, should conduct collision avoidance and passivate objects after operation, which means vent residual fuel from tanks, vent pressure tanks, and discharge batteries to avoid explosions. They also stipulate that objects in LEO after operations should be moved into an orbit low enough to make sure that the objects disappear within 25 years. And when they re-enter the atmosphere, of course, we also must make sure they do not cause a safety risk on ground. For objects in the geostationary zone, a compromise is found by asking these objects to be moved into a so-called graveyard zone a few hundred kilometers above. Now, these are guidelines, and guidelines are voluntary measures, useful but voluntary measures. On international level, you will not find these guidelines being applicable. What we have on international level is the Outer Space Treaty, first of all, which asks states to supervise and authorize the space traffic occurring from their countries. So in other words, on international level, responsibility for the monitoring and supervision of space traffic is delegated to the states. But since 2 years, we have the 21 guidelines of the United Nations, which are again guidelines, but which provide useful consensus of more than 70 states on how the supervision is to be done. And among others, they also ask, consider in your national laws the IDC debris mitigation guidelines, so that through this process, voluntary guidelines actually become applicable law. And since this is a process that is mandatory to be done for all countries where spacecraft on the space flight is emerging, ESA, with its expertise, is available to help and support this process of national law generation through experts, but also the ECSL body that it features. But of course, ESA itself is an operator and a launching state, but we do not have, of course, laws. Our equivalent to the law are admins issued by our Director General. And in our case, the Director General makes applicable the ISO 24113, which is based also on the IDC debris mitigation guidelines. And not only this, we also have a handbook that gives a detailed description on not only what is to be done, but also how we have to implement it. And since we believe that this might be useful also for the community, everybody can have this document, and it is available from ESA. And then, of course, we need to follow it ourselves, and we are very proud about ERS-2, our Earth observation satellite, which after 15 years of operations deorbited from 800 kilometers to 500 kilometers, reducing the lifetime by more than 100 years. Now, it's not enough to ask for implementation of mitigation. We also need to provide supportive tools. And the ESA software, we decided to make it publicly available. There's a drama suite which allows you to assess the risk on ground, which allows you to assess how much fuel you need for collision avoidance maneuvers, and many other useful tools. There's a master risk assessment software that looks at your impact survivability in space, and a database containing more than 40,000 objects, each of them characterized with its physical properties like mass, dimensions, and shape, and so on. And this can all be accessed through the link that is given here above. Providing and sharing information is one of the responses of ESA to the sustainability of the environment. Now, we have been talking about the mitigation measures and guidelines. Let's now look at how well they are actually followed. And there's a space environment report published by ESA every year, from which we take these statistics. And this statistic here is for LEO and the disposal of LEO objects by active maneuvers. And we see that the trend of the share of objects actually managing to successfully implement such a disposal maneuvers is pointing in the right direction. But the overall achievement at maximum is 50%, which compares to a guideline of 90% as prescribed by the ISO 24113. Now, this is, of course, a very poor result, but let's take a look further and also look at the number of breakups. These are the number of breakups and also the root cause, at least suspected root cause of the breakups in 5 years bin. And if you take the average, you will see it's around 10 per year, and this is still happening today. Part of the explanation, despite of the fact that we have passivation in place, is of course that also older objects launched several decades ago can still explode today. But clearly, also in terms of passivation, we seem to have a problem. And the reason for that, in my view, is not lack of regulation, because we know from simulations that the guidelines that are in place, they would do their job if they are adhered to. We have, and that is my conviction, we have a problem of adherence. And that adherence is not only bad will. Of course, we also need measures to better follow up the implementation even after launch. So once an object is cleared for launch, we need to continue following up the robustness of the object to implement all these measures. But it is also a lack of technology, because a lot of these breakups and a lot of the failed disposals are due to complete failure of the space system in space. When losing communication, when losing power on a space bus, you cannot command it to passivate nor to dispose, even if it is designed for it and even if it has enough fuel. So we need to take the technology to overcome it. Now, if we continue to do spaceflight without mitigation, the number of objects above 10 centimeter would follow roughly this trend over the next 200 years. And you see a cascading effect coming in through the fact that the curve is slightly bended upwards. If we manage to successfully implement passivation, we would cut the problem by half. And if we combine successful passivation with successful post-mission disposal to at least the 90% prescribed by the standards, we would stop the growth. And this shows that the guidelines are working. We don't need to reduce 25 years to less. We just need to follow the 25 years. And for this, we need technology. Now, if we want to not only stop the trend but revert it, we will need to do active removal, because that would finally stop the cascading effect that is still going on in the background because of the high number of objects that is already dysfunctional and out there. If we continue the trend of doing a bit of mitigation as we do as per the statistics I showed you before, we would end up with a red curve, which is very close to doing nothing. So if that trend is followed, we will be heading for a disaster. Now, I said technology is the solution. We have a lack of mature technology to implement mitigation robustly, even in case of failures. And to overcome this problem, already 10 years ago, in ESA, the Clean Space Initiative was founded. And the Clean Space Initiative looks at building blocks and technology to make passivation fail-safe, to passivate a tank, to passivate a power distribution unit and disconnect solar generators from the bus, even in case of system bus failures. And these building blocks need to be available when mitigation rules are tightened, so that our industry is actually prepared to follow them. Also, we need to work on a better implementation of post-mission disposal. And also here we are looking at redundancy by, for example, looking at deorbiting kits, which can be mounted before launch, providing its independent communication, providing its independent propulsion, even so that even when the main bus fails, a disposal can still be commanded from ground and actually successfully implemented. Design for demise goes back to our observation that we do have typical survivor objects, like in particular tanks, but also batteries and reaction wheels, magneto-torquers, for which we would like to develop demisable versions. You see here some under test, so that we can afford to fly platforms in space for an uncontrolled re-entry, which saves a lot of cost. Now, we are also convinced that in the future we need to go also on towards active removal, and active removal is easier when the target objects are prepared for the removal, and that means they need to be trackable from ground so that we can see their position and also their attitude before we even launch the removal vehicle. And we also need the rendezvous markers on board in order to ease the access to the object, and then of course a mechanical docking interface so that our arms, robotic arms and other docking mechanisms can actually grab them. And that brings us to the topic of active removal itself. And here we are happy to present that ESA, together with our partner ClearSpace in Switzerland, is preparing the first ever removal object of a piece of debris that is already in orbit as we speak. It is an element of an upper stage called Vespa, with the mass of roughly 100 kilogram in 700 kilometers altitude. So it's a meaningful object. And ClearSpace will design a mission that will approach that object, grab it with 4 robotic arms, which brings several advantages, and then safely dispose it by the end of 2025. We have given ClearSpace a lot of freedom in designing this mission so that they can prepare this mission not only for ESA, but also towards the market. We believe in the development of a commercial market. Now, who would be paying for that? We believe that we need to demonstrate that these kind of missions can be conducted and can be repeated at a reasonable price level, recurrent price, because only when this is demonstrated successfully, then regulators will pick it up and actually try in future versions of space laws to ask spacefarers to remove their object by using an active removal service when they have failed to remove it with its onboard means. And that would create an incentive for these spacecraft to better implement post-mission disposal right from the start, and for the leftovers to use to create a market for these removal services. But for this, removal needs to be demonstrated, and that's what the space agency is for. Now, we are often asked, why are you removing large objects while we have so many small objects out there which are much more numerous and which are much more likely to kill a spacecraft? Now, let me explain the answer for that. If you have a large object in 800 kilometer altitude, it has a fairly long on-orbit lifetime, roughly 100 years. The smaller the objects are, 10 centimeter, 1 centimeter or 1 millimeter, the shorter the on-orbit lifetime, because the smaller they are, the more sensitive they are to the atmospheric drag of the atmosphere, and they will disappear from space more quickly. Now, if you put all these 6,000 large objects in the box, you end up with something of 100 meters size and 8,000 tons heavy. If you put all the 30,000 10 centimeter objects in a box, surprisingly, this gives a smaller box of just 10 meters size. If you put the 1 million 1 centimeter objects, it gets an even smaller box, despite of the many objects. And for the 150 million 1 millimeter box, it is even smaller. And these are removed by the atmosphere after a while. But as soon as one of the large objects is involved in a debris generating event, we immediately reproduce hundreds of thousands of the small ones. So, in other words, the large ones are the source of the small ones, and we need to tackle the source. We need to get out the large ones in order to prevent reproduction of small ones and leave the work of cleaning the atmosphere from the smaller ones up to the natural forces of the atmosphere. Upon active removal, we see as a very first stepping stone towards even more ambitious mission. Rendezvous and capturing an object is the very first element, but once you do that and once you master this, we can go to the next step, which is the actually manipulation of the object, refueling, AOCS, or perhaps even smaller repairs. So this is what we call in-orbit servicing, which for us is the natural evolutionary step after active removal, followed by on-orbit manufacturing and assembly, the most ambitious goal that we have in the long term. Now, to close out, let's come back to the emerging space traffic of the very recent past. Now, we were used to launch rates of roughly 100 launches into LEO over the whole history of spaceflight, fairly constant, and this is changing now radically. Now, in the past years, we had close to 400, and then for the first time, we had more than 1,000. And if you take into account the plans for launch in the next few years, we will have launched more than all humanity has launched in the whole history of spaceflight in just a few years. And this, of course, is a radical change, which puts a new challenge, because this raises the question on the capacity of space. Some orbital regions might be heavily used as compared to others, and it might shy other users away from using the same altitudes, which creates a new challenge. And here I would like to offer the notion of considering space as a limited and a shared resource that has a certain capacity that cannot be exceeded. If you compare that to the frequency spectrum, you will find several similarities. Also, the frequency spectrum is limited, and but this is coordinated. So whenever a new mission is launched, it will not like to interfere with others. So it will make sure a coordination is happening. And in the coordination process, several competing missions for the same frequency will try to share the available frequency space by most efficiently using it. And this is done through a coordination process. I'm convinced the same can be done with space. The capacity of space is less obvious but we can make it visible. And ESA, together with international partner, is developing concepts to compute the so-called environment footprint, which is our equivalent to the capacity use, which will actually make transparent how much of the space capacity is actually consumed by a mission. It can be computed in a transparent and open process. And once this is available as a tool, I think it can be offered to the community as a future tool for also the coordination of the use of space, not in order to prevent anybody from going to space, but to share the available space as efficiently as possible. And with this, I thank you very much for your attention and wish you a successful conference.